Hey, BC Calc, this is going to be your day 56 notes. Today we're talking about some continued volume here. And specifically, we're going to see some examples that now have a delta y instead of a delta x. So thinking about spinning and revolving our regions, our areas around the y-axis instead of the x-axis. Of course, it's a possibility in terms of a solid of revolution here. So there's an area practice question about finding the area between two curves, and they happen to be two of our favorites, y equals sine x and y equals cosine x. So it says find the area of the triangular region. Notice the quotes there because it's not really an exact triangle, but you'll know what I mean when you sketch it in the first quadrant bounded by the y-axis, and then these two functions, sine x and cosine x. So sketch a picture there. See if you can find the area between those two curves that apparently looks somewhat triangular, and we will go over that next time we are together in class. So taking a look at a recap of the disk method here. So disk method from day 55, it's the concept of taking that plane area, swinging it around the x-axis. I think this visual really does a good job to show you all these little disks that have an area whose radius is along the height of the function. The thickness is that delta x component, which changes over to dx in our notation for finding the definite integral there. But because we have all these circular regions, what we're doing is we're taking pi times the radius squared. The radius, again, is the height along the function, times the thickness, delta x. So as we kind of build towards our formula, if you will, for the volume using the disk method, we can take that pi out as a constant, times the integral from a to b of the function f of x squared dx. So we're just going to a little bit more practice today in this lesson with using the disk method. And if we turn to the next page, the first example you'll see is we're going to rotate something around the y-axis. So if we sketch what we got going on here, find the volume of the solid generated by revolving the region enclosed by y equals radical x, y equals 2, and x equals 0 around the y-axis. So here's what we've got visually. Okay, so y equals radical x looks like this, right? And then we got the line y equals 2. So that might be something like this. So here's radical x. Here's y equals 2. And the line x equals 0 is the y-axis right here, right? So here's the line x equals 0. What I want to do is I want to take this region right here, and I want to spin this around the y-axis. So we're going to spin it around that way. So you can imagine that if I were to spin this around this curve, y equals radical x, it's going to kind of have a repeated curve over here. And the disks in question would be these circular regions going across through the y-axis there. All right. So if we're going to find the area of these circular disks and then multiply it by the thickness dx here, what we have to do is, since we're integrating with respect to y now and revolving around the y-axis, we have to get the equation y equals radical x as x in terms of y. So instead of y equals radical x, we would have that x equals y squared. Okay, so another way to think about this curve, x equals y squared, because the radius here going across horizontally there is the radius horizontally to the function x equals y squared. And the bounds of my integration, when we integrate with respect to y, have to be along the y-axis. So we know that the bounds are going to be from 0 to 2, since we're bound by the line y equals 2. So therefore, if we pull the pi on the outside, it's going to be the integral from 0 to 2 of, this is the function that we're finding the radius along. So it's pi radius squared, so y squared squared, and then times our thickness dy. And this is going to be a pretty easy integral for us to calculate, right? Because it's going to be from 0 to 2 of y to the 4th dy. So then if I use the anti-power rule, it's going to be pi times y to the 5th over 5 from 0 to 2. Plug in the upper bound, plug in the lower bound, and you're going to wind up in the end getting 32 pi over 5. And since we're talking about volume here, we are talking about cubic units. So this whole idea in chapter 6, we kind of go back and forth between the concept of areas and volumes. Now, when we integrate area, we're finding the sum of all of those areas, so we're generating a volume here. okay? But make sure if you're going to label units, and I would like you to label units, that you're using the appropriate labels here. Okay. Here's another interesting example. For the most part, we're going to be revolving around the X and the Y axes, but certainly we can rotate around something like the line, and actually I'm going to change this for you. Okay. We're going to rotate around the line Y equals 2 in this example. So it says rotate the region from the example above around the line Y equals 2, and then find the volume that's generated there. Okay, so if we were to sketch that picture again. Okay, here's my function Y equals radical X. Here's the line Y equals 2. Okay, that's the line that we're going to rotate around. So if you imagine taking this shaded region right here and rotating it around this horizontal, you're going to get this curve to appear up here. Okay, and in this case, all of the disks are going to look something like this. Okay. So because of the way that I'm drawing the disk here, we're going to have this, because the disk is vertical in this case, because we're swinging around a horizontal line, we're going to integrate with respect to X in this example. So the bounds for the integration are going to be from 0 to, well, remember this is Y equals radical X. So if Y is 2, then X would have to be 4. So the bounds for integration are from 0 to 4. And then the only other thing you have to think about here is pull the pi on the outside, pi r squared. What is r in this example? What does the radius equal? So the radius is going to be, if we think about this radius right here, the way you can find that radius is you're going to take the difference in the height of 2, and you're going to subtract out the height to the function radical X. So at any given point, if you were to find a disk along the way, the radius of that disk would be the height compared to 2 minus the height of the function radical X. So the radius at any given moment is 2 minus the square root of X. Now, because we're finding the area of that circle, the radius is going to be then squared down here, right? 2 minus radical X squared dx. And then from there, we can go through the process of finding the value for that definite integral. So when you square this, just be cautious about the algebra there. So if we multiply that by itself, you would get 4. You would get a minus 4 radical X in the middle, and then plus X at the end for squaring the radical X dx. Use some quick anti-power rule here. So that's going to be pi times, this is going to be 4x. This is really x to the 1/2, right? So if I up that, that's now 3/2, which means if I divide by 3/2 up front or multiply by 2/3, it's going to be minus 8/3 x to the 3/2. Again, that's just why I'm saying be a little bit careful about the algebra in your head. And then x squared over 2 for the end, over the bounds from 4 to 0. All right. So plugging in all the appropriate bounds, plugging in 0, the nice thing about the lower bound is, again, this whole thing becomes 0, so I don't have to worry about subtracting out that lower bound. But when I plug in the upper bound of 4, it's going to be 4 times 4, which is 16, minus 8/3 times 4 to the 3/2. Let's see, square root of 4 is 2, cubed is 8, so it's going to be minus 64/3 in the middle. And then at the end, plus 8. And of course, along the way, we might want to use a calculator to double check some of our operations here. But in the end, once you combine all like terms, get common denominators, the volume that we're generating here is 8 pi, and this would be over 3 units cubed. Okay. So the toughest part about this one is just really thinking carefully about how do we define the radius, specifically when you're rotating around a new line in the plane like y equals 2. And I think this visual and drawing the picture is really where it's at. Okay, if you don't have a good picture drawn, it's going to make it much tougher to determine what that radius is. But again, it was the total height of 2 minus this height up to the function radical x there. Okay, perfect. It's a pretty short lesson. We'll do some practice next time we're together, of course. So we're going to preview a new method right now by thinking about what if I were to rotate the region in the last example. We really love y equals radical x today. What if I were to rotate it around x equals 4? What would that look like? Well, so if we think about the example that we just sketched, where we had y equals radical x, we were bound also by y equals 2. Here's y equals 2. This is y equals radical x. And we know that they intersect at the point 4, 2. But now I want to spin it around the line x equals 4. So can you imagine taking this shaded area right here and spinning it around the line x equals 4? What would that result in? Well, you would get kind of what looks like, I don't know, I guess the way I would describe it as a bridge almost, two-dimensionally. Right? You get this shape right here. So if I kind of reflect this over here, we get that shape, but the idea of finding the volume in this case is if I think about spinning this region around, that three-dimensional surface is going to start to look like maybe like an empty like bowl, like a cereal bowl or something like that. So to find the volume, what we're going to have to do is think about that when I take a cross section across here, you're going to get this shape right here. So if I go from 0 all the way across like this. Okay. So it's not quite a disk, because what happens is the disk would have all filled in closed space in between. What's actually happening is you get this open area in the middle with no volume at all. So we're getting these regions here that are going to be slices with kind of an open piece in the middle. So this is not a disk. If you look ahead in the lessons, you'll find out pretty quickly this is something called volumes by washer, okay? So if you think about, if you know what a washer looks like, a washer has that empty circle in the middle, okay? So we're going to talk about in the next lesson, how do we find the volume in this case, but I think you could probably, looking at the picture, generalize it that the area that I want to capture and then spin around is going to have to deal with the radii of both of those circles. Okay, so if you think about the connection between those radii, I think we'll be able to generate that volume as we spin it around that line. So we'll get into that in the next lesson, but last thing I want you to do is try this one. So it says calculate the volume of rotating this area around the x-axis and y-axis separately. Which one is larger? So first you're going to rotate it around the x-axis, then you're going to rotate it over here on the y-axis. Okay, you don't need a function at all. Just think about what's going to happen if you rotate that rectangle around and generate those volumes and compare them and see which one's larger of the two. So pretty quick day 56 lesson, more disk method to come. We'll do a little bit more practice with revolving around the y-axis since that's a little bit new in this lesson. And have a great rest of your day.